relax very slowly, whereas all the boring bulk transport that you don't want to see will actually relax quickly because it's tied to the charge imbalance. So that's the kind of physics we're going to try and explore. So I'm always going to think about physics in the limit where the valley is a much more long-lived degree of freedom than the charge, in effect. So this experiment is sort of very simple. It basically consists of taking a slab of wild semi-metal, and I've drawn a sort of idealized version of this experiment. Many of the idealizations can be removed and you'll still see something interesting. The idealized version of the experiment is that you pass current through the sample with a magnetic field oriented parallel to the current, and you screen the sample from magnetic field for some time. And this is just a technical detail. And at some distance further away, you measure a voltage. And it turns out that you'll see a voltage only in the presence of an additional magnetic field placed near this probe contact, near these probe contacts. There won't be any voltage in the absence of the second magnetic field. And so this is a thought experiment. Of course, this is not the most easy system to, this particular setup may not be the easiest to realize, but let me just tell you where this comes from, these ideas come from. The basic idea is that I'm imagining this setup where I have a source and a drain and I have a magnetic field, and I'm going to try and generate a valley imbalance from the source and the drain. So again, let me remind you that in this material you have the lambda levels of wild semi-metal. So you have this picture here. And now let's imagine I pass a source drain current. Now this is a system which has a conductivity. So if I pass a current through it, there's going to be an electric field in the system. And that's going to lead to this imbalance between the right and left chemical potential. So what's going to happen is that a current moving from source to drain over here is going to be reflected as a valley imbalance. So mu right minus mu left will be proportional to this current flow. Now, as I said, the valley imbalance diffuses. There's no way you can just keep it in this region. So the valley imbalance is thinking of it as a hydrodynamic variable, will just diffuse through the sample, and will diffuse while relaxing at a rate set by the valley relaxation length. So it's diffusing through the system, but also relaxing on a length scale set by Vs tau d. So this is just the valley relaxation length here. And what I'm going to do here is try and measure the voltage by putting probes contacts here, because I've got something diffusing across the sample. Now, the key point is what's diffusing across this is a valley imbalance, which naively has nothing to do with the charge, except that if I put a magnetic field here, so in the presence of this magnetic field, essentially what happens is if I see a valley imbalance come in, it's equivalent to having a charge flow across the sample. So if I'm sitting over here and my detector is just a pair of contacts, I see this situation where I see this imbalance between left and right handed, between the right and the left nodes. That means there's a net current flow in the up direction here. So basically the valley imbalance leads to a Z current and hence a Z voltage, and therefore there's a non-local resistance associated with this valley imbalance. So the question is, why does this test anomaly physics? The idea is that the bump contacts give you a top-bottom. So just because of the fact that I put contacts on a sample, there's going to be resistances everywhere because it's a metallic sample. But if you just think about the fact that I'm thinking of a limit where there's a short charge relaxation length, then transport within this metal is essentially ohmic. And if you have ohmic transport, you can just apply Maxwell's equations, and what you find is that the ohmic contribution to any such resistance that I measure between the top and the bottom is just linked to the source drain voltage, of course, but it decays very quickly on a scale set by the thickness of the slab. And that you can think about because the only scale in Ohm's law is the boundary conditions that you put on it, and so the only scale in this problem from the point of view of Ohm's law has to be the fact that you have a slab with a finite thickness. The valley imbalance, on the other hand, decays over a much longer scale, and that scale is set by the valley relaxation length. And so basically, if you think of a length scale where I think of a thin slab and I think of a slab with a long aspect ratio, I can be in a limit where the slab is very thin compared to the valley relaxation length, and which is still of the order of the length of the sample. And so you can expect that the ohmic contribution is zero, but you see a non-ohmic contribution from this valley, from the valley relaxation, from the valley transport. Now, the basic idea is that we've used the anomaly to turn charge into valley degrees of freedom. And this is impossible if I rotate the magnetic field 90 degrees, or turn off the magnetic field, if you like. So the basic idea is that this valley imbalance is very sensitive to the presence of a magnetic field. So even if you're not in this idealized situation, you could actually end up in a case where you can separate an ohmic contribution by subtracting zero field effect. What I showed earlier was a pump probe experiment, and this just helps. There's a kind of trick you can do. If you didn't have a field in here, it turns out the imbalance over here can be tuned by the angle of this field. So if you flip the sign of this field, you'll be able to just take the odd in B detector response, and that'll allow you to improve your signal. So it's just a proposal there to do that, but it's much hard. It's obviously quite hard to screen magnetic fields on short scale, so it's tricky to do that. You can model disorder, and I'm not going to go into the details of this, but you can show that for a modest level of doping of the vial semimetal, you do indeed get a large separation of scales. If you take a short mean-free path of the order of tens of nanometers, you can get a value relaxation length of the order of microns. This big separation of scales is not entirely unreasonable. You can also do a similar calculation of the Dirac semimetal. I'm almost out of time, so I'm not going to go into that, except to say that it turns out much of this physics survives in Dirac semimetals as well, where you have to be a little bit more careful because you're talking now about crystal symmetries and scattering between two different crystal symmetry states. But it turns out that a lot of this physics of large relaxation lengths for the anomalous contributions does survive there. And I'm not going to say much about this. About a couple of months ago, there was some very intriguing experimental evidence from a group that split between China and Australia, and they seem to see a very small field-induced non-local contribution in cadmium arsenide. It's very early days yet. There are possibly a lot of alternative explanations, but they have done things like turn off the field and look at the background and see what happens. It is true that in this cadmium arsenide is known to have a very long mean-free path, and it turns out that if you look at the value relaxation they get a value relaxation length that's more than the mean-free path in that sample. So it seems like the separation of scales isn't really operating there because the sample is so clean that the value relaxation length is pretty long in cadmium arsenide, known for its very high fidelity. So I think that there's not yet any smoking experimental gun signature at this point, but it seems that these kinds of experiments are not beyond the realm of feasibility. So I think I'll stop there and leave my summary up. Thank you.
Questions? Just to remind everybody that if you have a question, you wait for the mic because we record it. Any questions?
Just to clarify what you said about the Dirac semimetal and fermion.
Yeah.
So I suppose the next speaker will clarify this issue, but since you are giving the first talk, I just want to make it clear I understand it clearly. So if you have a Dirac fermion instead of vial fermion, then the Gaussian be around that point and Chern number is 0.
Right.
So it's not obvious that you should have a fermion, say, between two Dirac points.
So what you can do is you can ask a question like a symmetry filtered Chern numbers. You can ask about a Chern number of some particular crystal symmetry sector, as I understand the way you calculate it. And to chime in if I'm saying something wrong. But yeah, you can ask about, for instance, for topological crystalline insulators, there are things like mirror Chern number you can define. You can define a similar thing for a particular crystal symmetry eigenstate. You can ask about the Chern numbers of a particular crystal symmetry sector. And that's the thing that and as long as that symmetry is preserved, you can't remove that. So that's the symmetry that protects the existence of the argument.
But then how I should think about your argument if I take the cut?
So, very good. So then you have to take a cut on a surface that preserves that crystal symmetry. If you don't have a surface that preserves the crystal symmetry, you won't see anything. So it's a little less robust, I think. I think Andrew's going to talk a little bit more maybe about that, because there's some subtleties of exactly what surfaces you see in art versus not. So, okay.
Yeah, in this envelope transport proposal, I guess, at least I didn't notice you say anything about what regime one needs to be in as far as the megacy tau, various taus for different. Usually, doing transports, one small, large, taus.
Right. I think you can essentially be fairly so. So for the non-local transport, I think even at very weak fields, you'll be fine. So you don't need to be in you don't need to be in very, very high fields. So you don't have much of a constraint in omega C tau in this problem because you can sort of play with the geometry in a way that, if you think about the slabs and the geometry I wrote in, if you think about where your cyclotron orbits are, they're not, if the field's going that way, you sort of can ignore some of the cyclotron orbit physics. But I agree that there's this issue of a skip orbit on the surface that can give you some of this non-locality.
Omega C times inner valley relaxation should be large?
No, I think it's omega C times the charge relaxation should be large. It's, not beta valley relaxation. Because you're not necessarily worried about the...
That's a larger tau, right? You want the inner valley relaxation to be the largest tau.
That's right. So I want omega C. Good point. I have to get back to you on that. I'm not sure I have a quick answer on that. I'm not sure that I need a constraint on, I'm not sure that I need any particular constraint on that. I don't think there's a particular notion of inter-valley relaxation.